Okay, so hello everyone, welcome back. Um, so before we begin with our usual lecture, like probably few quick announcements slash discussions. So first of all, your assignment one is available online. Like I think released it last week. So if you have not looked at your assignment, probably a little bit late already. So start looking at your assignment and start solving it. And I received before I say about the feedback, like one thing that I want to remind everyone again is there is an anonymous Google form in the course Moodle, like where you can go and give feedback about the lectures and assignments and whatever feedback you want to give to me, like after every lecture. Okay, so that form is available throughout the semester. So, and I do regularly check it and see if I can incorporate those feedbacks. So there was one feedback about. I think there's more feedback with the mic. Okay, there was one feedback about the first assignment. So I think the student mentioned it would have been easier if we give you all the template functions and you just choose like whatever bandit algorithm that you want to implement. Okay, I know we could have done that. Like, but I want to explain you like why we did not do it. Okay, so like part of your assignments is also like part of the goal of the assignment is also to like help you learn how to organize your reinforcement learning projects. Okay, so if you have done a machine learning course already, then you would know that a machine learning project is not just that piece of algorithm. It has a lot of things to do, like with starting from like how you checkpoint your model and like so like how you control your like randomness in the algorithm and how you organize the pipeline and so on, right? Like so the like one of the goals of the assignment is also like for you to practice all those things. Like so the goal is not just to implement epsilon greedy, but to see if you can set up a bandit experiment by yourself. Because when you have a real life problem, like a bandit problem, like which you want to use, where you want to apply these algorithms, like you should know how to transform the data. You should know how to feed the data to the algorithm, not just implementing the algorithm. Okay, so the goal of the assignment is also to like let you experience the whole pipeline, not just implementing that one function. And if you have more feedbacks, please go and write them. Like I'm always eagerly looking forward to read your feedback. And there was also another feedback that the second lecture was a bit difficult to follow. So how many of you felt it was a bit difficult to follow? Okay, so you and well, I think people can raise hand in part like Zoom, but it's difficult to count. Okay, so we hear a lot of surrounding noise. Well, it might be because people are moving. Okay, so the thing is like the mic is connected. There are two mics in the classroom, which is also connected to Zoom. So if you make noise, it's going to get recorded. So please try to not make noise. Okay, so well, if okay, so I will take that into account, and we will see how today's lecture is like. So if you still feel the lectures are difficult, like come talk to me. But in general, like this is a general tip for everyone, like not just for people who feel the lectures are difficult. Like try to refresh your memory about the previous lecture before you come to the current lecture. Okay, so try to at least read. I know that like it would have been easier like if I give you the lecture notes a week before so that you have time to read what I'm going to teach. But this is like a fresh course. Like as you can see, I'm really like developing the course on the fly. So it's difficult for me to give the lecture notes much earlier. But what you can do is read the lecture notes of the previous lecture before you come to the class. Like how many of you revise your previous lecture before coming to the class? Okay, a lot of you, which is good. Okay, keep doing that. Like so, like you have only one lecture per week, which is totally new for me. Okay, so like I am used to teaching 2 lectures per week, 1.5 hours. Like teaching one 3-hour lecture is a bit too much for me as well as you. So there's a very high probability that you will forget everything from the previous week if you have never touched it once again before the class. So try to like refresh your memory, and hopefully that will help. Okay. So, and also if you have any doubts, there are office hours every day, and TAs tell me that not a lot of students utilize the office hours. So if you have any doubts, like don't wait for the next lecture. Like, so there is one office hour per day. So if timing doesn't work for you on Monday, probably the Tuesday timing will work for you. Like, so there are different timings for Monday to Friday. So like, check when are the TA office hours and like go ask them your doubts. Get your doubts clarified before you come to the next lecture. Okay. And one last announcement before we begin, which is about the course project. Okay. So the course project details are not yet updated in the website. Like, so probably it will be updated today or tomorrow. I will send an email once it is done. But I want to give a very rough idea today so that you can start thinking about your course project. Okay, so before that, I saw a comment in Piazza. I don't know if it is for the oral course or for the ML course. I think it's for the oral course. Someone was asking for, like, looking for teammates, and they said we can help each other in assignments as well. Okay. So if you have read the instructions of the assignments, like all your assignments are individual assignments. You are not supposed to help each other in your assignments. Okay. So like if we find highly overlapping text or code, both of you will get 0. So like, so assignments are not collaborative. So like they are individual assignments and the project is collaborative. Okay. So now let's quickly talk about the project before we jump to the lecture. So we will explain in detail about different options like in the website, and also I'll send you an email. But roughly this is what we have in mind. Like, so, okay, so I think okay, so I wanted to show the website, but I can just tell maybe directly. So if you have already checked the website, so you are supposed to have an initial proposal of what your project is going to be by 6th week of the course. Okay, so then you have 1 month, and after that, like you have like an intermediate report, and then by the end of the 2 months, like you have the final report. And we will also have a poster session based on your project towards the end of the course. Okay, now I'll give you some ideas for the proposal so that you can start thinking about it. Like you have 3 to 4 weeks, I guess, left, but still, it's worth thinking about it. So there's going to be 4 tracks. Okay, so the first track is reproducibility track, where the idea is like you will take a reinforcement learning paper and try to reproduce its results. Okay, we will give you a list of papers, but you are free to pick whatever paper you want to pick. Okay. The reason why we have the initial proposal stage is just to make sure that you're in the right track. Like, so if you pick a paper that we think you cannot implement by the course period, we will say, okay, try taking a different paper. Okay, so the first task, like first track, is about taking a paper and reproducing it, like reproducing the experiments in the paper. And as we will discuss more towards the later half of the course, like reproducibility is a big challenge in both machine learning and especially in reinforcement learning. Okay, so you will find it really hard to take a paper and reproduce it. Like, so there are a lot of stochasticity involved, and most often, like, results are not reproducible, which is a bad thing. But that's why we have this track. Okay, and the second track is ablations and analysis. Okay, so in this track, you can take any standard reinforcement learning algorithm, like, okay, so or a paper which has the code already available. Okay, or for the first track, you should not take a paper which already has the code available, so then you're not reproducing. But for the second track, like, you can take a paper which has the code available, or you can also take any standard algorithm, like which is available online, and do some ablations and analysis and try to understand the algorithm much more deeper than what we have seen in the class. Okay, so these analysis has to be meaningful. So we will describe what is a meaningful analysis in the description of the project. But for now, this is a rough idea. And I think the third track is applications. Okay. I know a lot of you are interested in this course because you want to apply reinforcement learning in your research, especially if you are masters and PhDs who are working in other fields, right? Like so, like even for undergrads, like you may be interested in some like applications where there is scope for reinforcement learning. So this track is for coming up with your own applications. Like it could be a new environment, or it could be a new task, or it could be a standard classical task in a different field, like where like you show that you can actually learn the behavior using reinforcement learning and so on. Okay, so again, like when you write the proposal, you have to be very clear about what is the application that you're trying to do, why is it non-trivial, and we will help you shape it. Yeah.
Does it have to be a new application, or it's okay if someone already did it? But we don't copy it.
Well, if you're taking an already well-established application, then like probably I would put that under reproducibility.
But like for example, if you try to apply it in finance, for sure there's someone who already did it before.
Okay, well, as long as you also justify that what you're doing is non-trivial and not directly available somewhere, like I think it should be fine. But what I am looking for, we will also give you evaluation criteria for these tracks, okay? But what I am really looking for in the application tracks is some unconventional applications of reinforcement learning, or proposing some really challenging tasks or environments where state-of-the-art algorithms fail and so on. Okay, so now to do that, like you don't need to implement the state-of-the-art algorithm. There are a lot of standard libraries which has state-of-the-art algorithms. Like so, you could come up with you be the adversary and come up with this task where this algorithm would fail. Okay, so that's the kind of like projects that I'm looking for in applications. And finally, we have the research track. Where this is for students who are maybe already doing some research, like you might be masters or PhDs. For undergrads, like if you take this track, like you should know the expectations. So the expectations for the research track is you work on a research project in reinforcement learning, like and which is publishable. Okay, so that's the bar. So the bar for the research track is really high, and if you're taking research track, like probably you should talk to me. Like so, you could consider like using some of your thesis work if you're a master's or PhD, like for this research track. But you should really talk to me and get my approval, like if you want to do the research track. Okay, and for the first 3 tracks, it's 3 per team. Okay. There's no exception. Like you have to find teammates. Like we cannot evaluate 100 projects. Okay, but just for the research track, because of its nature, like given that you might be showing some of your thesis work, which is already with your advisor and so on, like so this could be from 1 to 3 per team. Okay. Again, I want to highlight that the bar for research track is really high when compared to other 3 tracks. Okay. So there's going to be more details and example projects available in the website very soon. Okay, and we will probably talk a bit about this every week so that like I can help you find a good project and use my office hours like after the lecture. Come talk to me if you have any ideas that you want me to go through. Any questions before we begin? Okay. Also, there were not a lot of attendance for tutorials. I assume that a lot of you are in both the courses, so maybe you attended the ML version of the tutorials. If you did not attend both the versions, and if you struggle with the course, it's probably because you don't have the necessary mathematical background, okay? So you should go and watch these tutorial videos. So maybe the tutorial videos are not yet up in Moodle. Like, I'm going to make sure that they are up in Moodle today. So if you struggle with the course, check your math background. And we already have probability and linear algebra tutorials, which are recorded, so we should have the recordings in the Moodle. Okay, let's begin. I think we took a lot of time for announcements. So, yeah. Okay, thank you for the reminder. So, because I missed a lecture, like recording a lecture in machine learning, I have put automatic recording. So every time I start the call, it's automatically recorded. I just need to make sure I don't mute. Thank you. Okay, so a very quick recap of what we have seen so far. So we started the course with the basic reinforcement learning problems, and we decided to focus just on the exploration versus exploitation dilemma, right? So in the last week, and to study just exploration exploitation dilemma without all the other challenges of reinforcement learning, we looked at immediate reinforcement learning problems, or in other words, bandit problems, right? Like so, and we discussed several strategies for like exploring in bandits. Like we looked at epsilon greedy, we looked at optimistic initialization, and we looked at UCB, upper confidence bound algorithm, and we also looked at gradient bandits, right? Like so, you can notice from your assignments, like you are implementing all these algorithms by yourself and comparing them. So you're going to have even more deeper understanding after you finish the assignment. So then we started with the full reinforcement learning problem, like where we just started to formalize the reinforcement learning problem as a Markov decision process, right? Now, what is a Markov decision process? Like it has three major components. Okay, can someone tell me what are the three major components? State, action, reward, right? Like so you have states, you have actions, and you have rewards, right? And specifically, we were looking at finite MDPs, okay? So throughout the course, our discussions will be based on finite MDPs, okay? With discrete, where everything is discrete. But continuous versions of all these things exist, but probably we will not see them much in the course. Like we will look at continuous actions, but the rest of the things we will not focus too much, at least in the beginning of the course, okay? So we have states, a finite set of states, and a finite set of actions, and like a finite set of rewards, right? And once you have finite set of states and actions, then you can actually construct the dynamics of how the world behaves by using the dynamics function P, right? So if you remember, the P function gives us some probability distribution. Okay, in this case, what is the probability that the next state is yes dash and I get a reward, given my current state is yes and I take an action A? Okay, so in some sense, this dynamics function captures how the world behaves. Okay, so given that I am in a current state with some, and I take an action, like what would be my next state? Like what is the probability distribution for my next state? It's a discrete probability distribution because we have a finite set of states, right? And similarly, like what is the probability distribution over the reward that I will get given that I have taken this action? Okay, so now this is what we will call as dynamics function. Okay, and we also discussed about the Markov property. Right? So the Markov property says us that the probability of ST-RT given ST minus 1, AT minus 1, right? So this probability of what would be the next state and reward given my current state and action, right? Like so this should, like, by just conditioning on the current state, you should be able to make an accurate prediction of the next state and the reward. Okay, or in other words, the current state encompasses all the information that you need from the past so that you can make accurate prediction for the next state and reward. Okay, now as we also discussed in the previous lecture, like, so this is more, this is not a restriction of the Markov decision process itself. This is more of restriction on the state representation, right? Like, so like this basically tells us that if you can construct a state representation which captures everything from the past, then we have efficient algorithms available, like in the MDP setting, like which we are going to see today, tomorrow, like today, next week, and probably at future weeks, right? Like, so, and we can utilize them, and we have some guarantees for finding the optimal behavior. Okay. Okay. Now we also discussed about like two types of problems, right? So in one side, like we had episodic problems where the interaction with the world ends in a definite, a finite amount of time. Okay, it is not definite, but a finite amount of time. For example, is playing the game of chess. Like, so when you're playing chess, it is like playing, you start playing, and then like at some point somebody is going to win or lose, the game ends, right? So the interaction ends. Now you can repeat this as many times as you want. You can play the game as many times as you want, but these are different trials or episodes. Okay? So now that is episodic. So in episodic problems, the interaction ends. Okay, and then we had, I think, continuing tasks, right? In continuing tasks, the interaction never ends. It is like a continual problem. Okay, can someone give me an example for a continual problem? Yeah.
The stock. Investing in stock.
Okay, investing in stock. You don't want to stop, right? Like, so you always want to improve. Yeah. Sorry. Cart pole. Okay, so well, probably we have not seen cart pole. Like it's a balancing task, like where you want to balance the cart pole, which means you have to keep on balancing it. It doesn't stop. But there is end to the episode. Like if you go down, like then the task is done, right? So, for example, keeping this room clean, right? So if you have a robot which is keeping this room clean, like its job is to always keep it clean, like so. So this task never ends. So there are a lot of interesting problems where there is no like episodic notion. Okay. However, there are also a lot of other interesting problems, like where you can frame them as episodic tasks. So there is value in studying both these settings. Now we discussed about like how to define cumulative reward, or in other words, return for episodic problems and continuing problems, right? Like in the case of episodic problem, we know that it is going to end at some point. So my return GT is defined as RT plus 1, RT plus 2 to RT, right? So the cumulative reward or my return is basically whatever the rewards I'm going to collect starting from now to the end of the episode, capital P. Okay. Now, this has a problem when you are in continuing setting, right? Like when continuing setting, if you define your return this way, then that return is infinity, because you just sum infinite number of rewards, and this return is going to be infinity. Okay. So we discussed an alternate notion for discounted returns here, right? Like so in this case, my GT is going to be RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3 and so on. Okay, or a concise way of writing this is like summation k is equal to 0 to infinity gamma power k. My R and gamma are really confusing in the notes, so I will fix it for the next edition. So gamma power k RT plus k plus 1. Okay, so where this gamma, which is between 0 to 1, Okay. Oh, I think there's a mistake in the notes. It should not be less than or equal to, like it's less than 1. Okay. It's called the discount rate. Okay, it's not a mistake. So, well, you can have equal to 1, but then when you have gamma is equal to 1, it becomes the undiscounted setting. Okay. So if gamma is less than 1, then we discussed like what does it mean, right? Like, so in some sense, like one way to understand discounting is like through the money analogy that I gave last week, right? Like, so like how, like it is $1 million today is more valuable than $1 million 10 years later, right? Like, so like anything that you receive in the future has less weightage when compared to what you're going to get right now. Okay, so like another way for looking at it, like for robots, is like it is important they live today, like and not die today, than focusing on something that is going to happen next week, right? So nearby events have more significance, and that is captured by gamma. Okay. Um, okay, so now there is also another recursive way of writing this. Okay, so let's look at that because we are going to use that in a lot of places today. Okay, so now let's take GT, which is basically RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3 plus gamma cube times RT plus 4 and so on, right? Now, I can slightly reformulate this like as RT plus 1 plus, I take one gamma out of the rest of the sequence. So gamma times RT plus 2 plus gamma times RT plus 3 plus gamma square times RT plus 4 and so on. Okay. Now, can someone tell me what this term is? It's GT plus 1, right? So now I can just simply rewrite this as RT plus 1 plus gamma times GT plus 1. Okay. Now this gives us a recursive or incremental way of defining GT. So like if I want to compute the return from the current state, so this equation tells us that it is basically the reward in the current state plus gamma times return from the next state. So this makes sense, right? Like, so like it naturally decomposes. Like, so now this is going to be helpful when we are implementing the algorithms that we are going to see today. Okay, so like we'll just make it as a note here that like you can write this in this recursive fashion, but we will use it later. Okay, so one quick note before we continue is, so in continuing tasks, okay, even though the sum is infinite, right? Like, so it's gamma times RT plus 2 plus gamma square times RT plus 3 plus gamma cube times RT plus 4 and so on, right? So there is no end period here. Like, so even though the sum is infinite, okay, so the sum of rewards is infinite. Okay, sorry, sum is not infinite. So even though it is a sum of infinite number of rewards, okay, the sum is still finite. Okay, it is because of the gamma term. So the gamma term is exponentially decaying the weight, like the importance of the future. So maybe after 100 time steps, like you will automatically have the soft end of the episode. It's not hard, but it is soft in the sense the weightage that you are giving to 100th time step in the future is close to 0. Okay, for all practical purposes, you can just say that the episode ended there, right? Like, so now, like as an example, for example, let's say if you always get a constant plus 1 reward, you get plus 1 plus 1 plus 1 infinite times. Okay, so then my GT would be summation k is equal to 0 to infinity gamma power k, right? It's going to be 1 plus gamma times 1 plus gamma square times 1 plus gamma q times 1 and so on. And we know that this is 1 by 1 minus gamma. It's a finite, even though the sum is over infinite terms. Okay. Now, So we have seen really two types of tasks here, like so episodic and continuing. Okay, and for both these tasks, we define returns in two different ways, right? Like now we cannot keep discussing like two versions of the algorithms like throughout the course. Like so, what we are going to do now is to just combine them and have one unified notation for return. Okay, so that is the notation that we are going to use moving forward, and that is going to capture both types of tasks. Okay, now again, as a recap, for episodic tasks, we have GT is equal to RT plus 1 plus RT plus 2 to RT. Now for continuing tasks, we have summation over k is equal to 0 to infinity, gamma power k, RT plus k plus 1. Right? Now, as we can see, continuing tasks are much more general than episodic tasks because they never end, right? So now, if we can convert episodic tasks to continuing tasks, some version of continuing tasks, then we have one notation for both, right? So, the way in which we are going to do that is very simple. Like, so we're going to take an episodic task. So let us say, I'm going to give you an example task here. Okay, so let's say we start with state 0 and we receive some reward, let's say plus 1, and we go to state 1. Okay, and then we receive some reward, let's say plus 1, and you go to state 2, and then you receive some reward. Okay, and the episode ends here. Okay, when the episode ends, I can just assume that you entered this dummy state where you always come back to this dummy state infinite number of times with reward 0. Right? So now this is a continuing task. So the reward sequence here is plus 1, comma, plus 1, comma, plus 1. If you stop here, that is episodic. So I'm just saying, okay, so I'm not stopping here. Like I will just have plus 0, 0. Okay. Now, if I view episodic task from this perspective, then I can just write one equation for return. Okay. So my equation is going to be summation over k is equal to t plus 1 capital T gamma of k minus t minus 1 or k. Okay. In this case, either t goes to infinity or gamma is equal to 1. As you can see here, if t goes to infinity, then this is the return for the continuing case, right? Like there is a discounting factor and t goes to infinity. If t doesn't go to infinity, then gamma cannot be 1, right? So if gamma is 1 and t goes to infinity, then you have this infinite term, right? So whenever t stops, then gamma should be equal to 1. Okay. Now there is also this another interesting setup, like can we have t goes to infinity and still gamma is equal to 1? Can we have undiscounted continuing tasks? Okay. Now it's a bit more complex setup. Like we are going to see such tasks and setups probably after a few weeks. Okay. But for now, we have this assumption that either t goes to infinity or gamma is equal to 1. Okay. Is that clear? So now this is like one definition for return. Okay, so far we have defined an MDP and the dynamics function of the MDP. Okay, so it's like we have seen MDP, dynamics function of the MDP, and we also discussed about return. Right? So what are the other important components of a reinforcement learning problem? So if you remember from our bandit discussion, like most of our learning is about estimating the value of the action, right? So just like how we had values of actions in bandits, we are going to have values of states and actions in reinforcement learning, okay? Because in bandit, it's a one state problem. There is only one state. So like you just had action values. But in reinforcement learning, we are going to have many states. So one can ask, how valuable is this state? Because I want to reach this state, like if it is highly valuable. Similarly, how valuable is to take this action in this state? If it is more valuable, then I'm going to take that action. Okay. Now, given that we are talking about states and actions, we should also talk about policies. Like, so my policy is basically, given a state, what should be my action? Like, so what should be my behavior? Okay. So there are two important topics. One is policies, and the other one is value functions. Okay, so almost all reinforcement learning algorithms that we are going to see in this course will estimate value function in one form or another. Okay, so the goal is to estimate value functions. Okay, now this value functions can be functions of state or state action pairs. Okay, now if it is a state value function, it tells us how good is the state in general. Okay, and if it is a state action value function, it tells us how good is it to perform this action in this particular state. Okay, now these value functions are often defined with respect to policies. Okay, now what is a policy? A policy is basically a mapping from states to probabilities of selecting each possible action. Okay, so we will write that as pi of A given yes. So this just means what is the probability of taking action A? Okay, so what is the probability of taking action A given I am in this current state? Is that clear? Okay, now let's talk about state value function first and then action value function. Okay, so state value function are represented as V pi of s. Okay, so what is V pi of s? V pi of s is basically value function of a state, yes, under a policy pi. So as you can see here, like we are defining value functions with respect to a policy, right? Like so, like a value of a state is determined by your future behavior, right? Like so, you go to that state, and what are you going to do in that state? Like so, if you don't know what to do in that state, like then probably no state is valuable, right? Like so, you should have a plan when you reach a state. So that plan is given by your policy. So we will always define our value functions with respect to a policy. Given that I have this policy, which is mapping my states to action, now is it a good idea that I reach this state? Okay, so that is what V pi of s is. Now V pi of s, okay, is given by expected value of the return gt given st is equal to s. Okay, so the value function of value of a state is an expected value of the return that I will receive from that state. Okay, and we know what is gt. So this is basically expected value of summation k is equal to 0 to infinity gamma power k rt plus k plus 1 given st is equal to s for all states. Okay, now this is the definition of value function. Now, one important note is the value function of a terminal state, a state where the episode ends, is always 0, because once you reach that, there is no more value, right? So V pi of terminal state is equal to 0. You don't need to learn the value. Like we know that if something is ending, then the value is 0 there. Okay, is that clear? Okay. Now, similarly, we can actually define action value function. Now we define how good is a state, right? So now let's talk about how good is an action in a particular state. So action value function. So action value functions have like a different notation, which is q pi of s comma a. So if you remember, this is similar to the q functions that we used in bandit setting, right? Like, so because in bandit setting, we were actually estimating the action values. There was no state, like there was only one state. So we were estimating the action values there. So what does this mean? So q pi of s comma a is basically the value of taking action a in state yes. Okay. Or in other words, what would be my expected return if I take action A in state yes and then follow the policy pi? Okay, that is q pi of s comma a. Now, q pi of s comma a can be defined as expected value of gt given st is equal to yes, at is equal to a. Okay. Now, just to compare with the value function of the state, v pi of yes, right? It was basically expected value of gt just given st is equal to a, yes. Right? We don't use actions in the state value function, but in action value function, what is the return I'm going to get given that I'm in the state yes, but I'm also taking this action A. Okay. Now I can expand this. This is expected value of pi summation k is equal to 0 to infinity gamma power k rt plus k plus 1 given st is equal to yes, at is equal to a. Is it clear? Any questions so far? So I know it's a bit, it might be a bit hard to follow because I'm introducing a lot of notations, but once we get into the algorithms, then it's going to be easier. Okay, so for now, it is important that like you are actively getting these definitions and notations. So there are a couple of questions in the chat. So I think one is an old question. Why can't you have t not infinity and gamma less than 1? Okay, that is a good question. So the question is, why can't you have discount factors in episodic tasks? Well, you can have. Like there's nothing wrong in doing that, but it also depends on your goal, right? Like so sometimes, like in episodic, okay. So the discounted setting can be seen in two ways. Okay, so one way is like to overcome this infinity problem. The other way is like practically maybe you don't really need to focus too much on the future, right? So I think it depends on the application. Like if you want to have discount factor included in episodic setting, you can have it. And in fact, we are going to use it in almost all the episodic tasks that we are going to see. Okay, yeah.
This is a slightly related question to that. So in the if you scroll up in the MDP that you defined with the dummy state, so if we have that dummy state that gives like rewards equal 0 for like essentially all of time, then why can't, like if we use that definition, like why can't t be infinity? And
why can't?
So like if we use the dummy state, right, where it's just looping on that dummy state for infinity, then t can be infinity as well, right? And gamma can be 1 because it's just after a certain point all the rewards will be 0, right? Like because wasn't that the point of the?
Oh yeah. Oh okay. So I think I think maybe I have to carefully swipe because if I swipe too fast, the video is affected. Okay. Okay, so I think maybe this was not a complete description here. Okay, so what I wanted to say here is when t is equal to infinity, gamma cannot be 1.
But if the MDP is defined as follows, then like you'll just have a bunch of like 0 rewards, right?
Well, if you know that it is an episodic task, then you can do that. But this is just a general definition, right? Like we don't know what type of task it is.
Right.
So then it is safer that you have t is equal to infinity with gamma, or gamma is equal to 1 with t is equal to infinity, right? Like, so now we can talk about other settings, like, so like, for example, the question asks, why can't you have discounted rewards, returns in episodic tasks? You can have them, like, so like what I wanted to highlight here is like what you can't have, but the rest of the combinations, like if it works, you can have them. And there's also another question: if you compute the expectation over the action. Okay, so first let me slowly move to the current slide. Okay, so this is also an interesting question. So if we compute the expectation over the action values, do we get the state value? Yes, there is a relationship between the state values and action values. Okay, so we are going to see that. So as you can see, the value of the state is considering all possible actions from the state, right? So it's basically summation over what is the probability of each action multiplied by the Q value of that action. So we are going to write that soon. Okay, now I want to highlight here that most of the learning algorithms that we are going to see are in some form going to estimate either V pi of s or Q pi of s combined. Okay, so once you have a good estimate of the value function or the Q pi, like action value, state value function or action value function, then we know how to behave, right? Like, so like given you are in a current state, like you can just consider all possible next states, and whatever next state has highest value, you take the action that leads towards that, right? So that is when you have the value function, state value functions. But when you have the Q value functions, it is even more simpler. You don't even need to do this lookahead search. Like, so given the current state, I have, let's say, 10 actions possible. And what are the Q values of these 10 actions? Pick the action which has the maximum Q value. Okay, yeah.
But the idea of using the state value function, it's not really possible in situations where you don't know what's the next state.
Yeah, that's a good point. So it is not possible when you don't have access to all possible next states, or in other words, it is not possible when you don't have the model of the world, right? So, but we are going to see algorithms where you have model of the world, in which case you can use these things. And in the future, we are also going to learn the model of the world so that you can use the state value functions. But it's a very good observation. Okay, now okay, now the next question is how to estimate these value functions. So we have already seen a technique in the past. So can someone give me an idea about how to estimate Q values or V values? Yep.
You start with a random value or at first, and then you update them. When you take, for example, action A and
Okay, but can you give me some other, like something that based on what we have already seen in the bandit setting? Yeah. Explore, no, I'm not talking, oh, we have the exploration issues, but I'm not talking about exploration here. So how to estimate V values or Q values? So like, how did we estimate action values in bandits?
You can show the previous values.
Sorry? Okay, any other answer? There was another, yeah?
You can take the previous values, average it out.
Yeah, simple sample averaging, right? Like, so you can just estimate these value functions by just recording returns that you get from a state. Okay, so for example, if you want to estimate the return of a state, you estimate the return, you estimate the return, estimate the value based on average of returns that you have seen from that state. Okay, and as we know from the bandit setting, as t goes to infinity, this average in expectation is going to be converging to the true value functions, right? However, this very naive sampling, like sample-based estimates that we have seen in the bandit setting doesn't scale well to reinforcement learning problems, simply because maybe we would have like millions of states or maybe billions of states, okay, or even more than that. Like, so in a complex problem, like for example, we are going to see some standard examples again and again. Like, so let's take the game of backgammon. Okay, so in the game of backgammon, like, so where one of the very first reinforcement learning algorithm was shown to work well. Backgammon has 10 power 20 states. Okay, so to estimate values of these 10 power 20 states by experiencing them is going to take thousands of years. So it is not always possible to directly do this simple approach that we are doing in bandit setting. So we would require some sort of like function approximation, but we will touch that probably after a couple of lectures. Okay, so probably I will stop here for a break.